Welcome. In today's lecture, we shall continue from where we left off, the interplay between the microcosm and the macrocosm. Today we shall use the ideas we developed in the previous lecture and return to a story of the inflationary expansion of the universe. But before we do that, let us try to recall what we are talking about. If you remember, in 1981, Alan Guth at MIT in Boston gave a plausible model for the exponential expansion of the universe. An exponential expansion of the universe was needed in order to understand the presently observed homogeneity of the cosmic microwave background radiation, as well as the fact that the geometry of our universe is flat or Euclidean. Now, what Alan Guth argued was that the grand unified theory phase transition, which, according to theory, should have occurred when the universe was 10 to the power minus 35 seconds old, could be one of those first-order transitions which correspond to a super-cooled transition of a vapor to a liquid. A transition in which the universe was temporarily trapped in a thermodynamically metastable state, or, as the elementary particle physicists would call it, in a false vacuum. Alan Guth argued that the exponential expansion of the universe occurred during this phase, when the universe was trapped in a metastable state or in a false vacuum. Before we proceed, let us refresh our memory about some of the important things I discussed in the previous lecture concerning the nature of phase transitions and the associated symmetry breaking with phase transition. If you remember, our story began with the famous paper by Lev Landau, published in 1937, on the theory of second-order phase transition. In that monumental paper, Landau introduced the concept of an order parameter. The low-temperature phase has a new property. It has a long-range order, which was absent in the high-temperature phase. For example, a liquid is translationally invariant, whereas when the liquid solidifies and forms a crystal lattice, there is long-range order in the arrangement of the atoms. To give another example, in a paramagnet, the individual spins can point in any direction they like. But at the transition temperature, at the Curie temperature, when the paramagnet becomes a ferromagnet, the orientation of all the spins align in a particular direction. So the spontaneous magnetization which appears in a ferromagnet is the order parameter. It has a non-zero value, whereas its value was zero in the high temperature paramagnetic phase. So this is the concept of an order parameter. Now what Landau said was the following. Look, boys, you forget about atoms and molecules and the Hamiltonian of their interactions. The starting point of a phase transition should be the thermodynamic free energy. Expand the free energy functional as a function of the order parameter, which I have called M. Unfortunately, the notation may not be consistent all the time. So here is the free energy expanded in powers of the order parameter. There is a term F0 of T, which is a function of temperature alone. Then there is a term which is linear in T minus Tc, where Tc is the transition temperature, and the proportionality constant is the square of the order parameter, and then there is a quartic term. The important thing for you to appreciate is that at a temperature greater than the transition temperature, the free energy as a global minimum for a value of alpha equal to 0, or order parameter m is equal to 0. So look at where I'm pointing the cursor. The free energy is a global minimum corresponding to the order parameter being equal to 0. But below the transition temperature, the free energy instead has a maximum at m equal to 0, but it has two distinct minima at a finite value of the order parameter. So let us look at this once again. So this is the same picture. So now let me explain in words. For t greater than Tc, that is the curve, for t greater than Tc, the free energy has a global minimum at phi equal to 0 or m equal to 0. Now what I have plotted here is phi as a complex variable. It has a real part and an imaginary part. In other words, I can represent it by a magnitude and a rotation angle theta in the Argand diagram. At t equal to Tc, a new global minimum appears at a finite value of the order parameter over there and over there. That is shown over here in this diagram to the right. This looks like a Mexican hat. So this is the global minimum, and it could be anywhere in the minimum in the azimuthal direction. And therefore, when the system jumps from this unstable maximum to this global minimum, the symmetry is broken. In what sense is the symmetry broken? Previously, the spins could be aligned in any direction they choose. But now, all the spins are aligned in the same direction. But that particular direction is arbitrary. It could be like this, it could be like this, it could be like this, it could be like this. So that corresponds to the azimuthal symmetry in this diagram over there. So one would say that when a system jumps from a paramagnetic state to a ferromagnetic state, the rotational symmetry of the Hamiltonian SI dot Sj, it is invariant under three-dimensional rotation, that rotational symmetry is broken by the ferromagnetic ground state. So I'm introducing the notion of a broken symmetry which is associated with this second-order phase transition. Some phase transitions are a first order, and they differ from the second order phase transition in that this transition occurs discontinuously rather than continuously, like in a second order phase transition. Now, if you look at this expression where I've expanded the free energy following Landau as powers of the order parameter phi, like before, there is a phi squared term or a phi fourth term or a m squared term or m to the power 4 term, but there is also a cubic term. It is the presence of this cubic term that makes a difference between first order phase transition and the second order phase transition. What happens in a first order phase transition is the following. An example of a first order phase transition is vapor to a liquid phase transition, or liquid to a solid phase transition. Now, what happens at this phase transition is that what is plotted here on the right is what are known as isotherms. And this dashed line is what is known as the coexistence curve. So let me explain. The y-axis is the pressure increasing vertically. The x-axis is the volume increasing horizontally. So let us say that this is the liquid phase. At high pressure, a gas liquefies, whereas as I reduce the pressure, at some temperature, it reaches the point on the iso coexistence curve where the free energy of the gaseous phase, which is the blue dot, is the same as the free energy of the liquid phase. So the free energies are the same at these opposite points on the coexistence curve. So at a particular temperature, if I decrease the pressure of a vapor, at that point, at that value of pressure, it makes a discontinuous transition from a vapor to a liquid, and we have a first order phase transition. In terms of the free energy curve, what happens is that the free energy of the vapor phase and the liquid phase are the same, and the system tunnels from the vapor phase, the liquid phase, in a discontinuous manner, and you have a first order phase transition. So a first order phase transition occurs when the free energy of the two phases become equal on the coexistence curve, and there is a volume change and there is a latent heat associated with the first order phase transition. I'm sure you are familiar with this from your pre-university physics. Sometimes when you cool a vapor towards the liquefaction point, at a certain temperature, I'm reducing the pressure of a liquid. At the point 2, the free energy becomes equal to the free energy of vapor, which is the point 4, and therefore I would expect a first order phase transition to occur discontinuously from the point 2 to the point 4 in this diagram. But sometimes, if an experimentalist is extremely careful, he can reduce the pressure of the liquid below the point 2 to what is known as the superheated liquid. In other words, ideally, from a thermodynamic point of view, this is a metastable state. It corresponds to the maximum of the free energy rather than the minimum of the free energy. So this is the superheated liquid. It should have become a vapor, but it remains a liquid. Similarly, on the other side, I can supercool a vapor. At the point 4, it should have become a liquid, but I can cool it and make it remain as a vapor by supercooling it. So this red point is corresponds to a metastable thermodynamic state. So a superheated liquid or a supercooled gas, excuse me, there is an error in the description there, are thermodynamically metastable states. They are marginally stable state. They correspond to the maximum of the free energy, or a false vacuum, as the elementary particle will call it, instead of the true global minimum of the free energy, which the particle physicists will call as the true vacuum. So in other words, the supercooled phase or a superheated phase corresponds to a maximum of the free energy. It is a thermodynamically metastable state where the system would like to be is in this global minimum. But for a while it can be caught in this metastable state or in this false vacuum. That is what we are interested in during the grand unified theory phase transition that Alan Guth was talking about. But before we go to that, let me make one other important point. There is a fundamental difference between a second order phase transition and a first order phase transition. In a second order phase transition, the new order, whatever that might be, is established everywhere. In other words, a paramagnet will become a ferromagnet over the entire sample. In other words, everywhere the spontaneous magnetization vector is pointing in the same direction. But in a first order phase transition, this does not happen. A first order phase transition occurs due to what is known as nucleation. So let me give you an example of what is nucleation. Now, here, let us consider a phase transition between water vapor and liquid water. As you cool water vapor towards the transition point, what will happen, if you observe the system very carefully, is that droplets of water will appear and disappear. The sizes of the droplets will grow. They will appear and disappear, till finally the whole thing becomes a droplet. So first, nucleation of the new phase occurs. If I take the case of a ferromagnet, for example, if it is a first order phase transition, then instead of the spontaneous magnetization being the same in all locations of the macroscopic system, you'll find that there are domains of ferromagnetism in which the spontaneous magnetization is pointing in different directions. Similarly, here is an example of an isotropic liquid, which is seen as black in this photograph. And what you have here are droplets of liquid crystal. It happens to be cholesteric liquid crystal. I'll say something more about it in a few moments. If you look at beetles in the garden, they have spectacular colors. The colors vary depending on whether you look at the beetle from the front side or the back side. These colors arise because the pigmentation on the shell of the beetle is made up of what is known as cholesteric liquid crystal. Cholesteric derives from the Latin word for color. So what you find is that this isotropic liquid crystal, the molecules are pointing in any direction they like, doesn't all of a sudden become liquid crystalline. First you see droplets of liquid crystals form, and then these droplets grow in size, merge, till finally you have a macroscopic liquid or a macroscopic magnet. So this is the concept of nucleation, which is characteristic of first order phase transition. All right. Now, as I described in the previous lecture, most phase transitions are associated with symmetry breaking. Let's look at some examples. The high temperature phase of a magnet, which is a paramagnet, is a more symmetric phase because the spins are allowed to point in any direction they like. Whereas that symmetry is lost in the low temperature ferromagnetic phase because all the spins will point in a particular direction. The direction may be this or that, but they all point in the same direction. But in the case of a liquid-solid transition, it is not a continuous symmetry which is broken or lost. It can be a discrete symmetry, like a translational symmetry is broken in a crystalline lattice. Now, breaking of a continuous symmetry is associated with second-order phase transition, and breaking of a discrete symmetry is very often associated with first-order phase transition. Now, the important thing to appreciate is that the low temperature phase, which is the less symmetric phase, has certain new properties which the high temperature phase does not have. And these new properties arise because the low temperature phase lacks the symmetry. So associated with the breaking or loss of symmetry is a new emergent phenomenon. So let's try to understand this a little further. So let's consider the paramagnetic to ferromagnetic transition. A paramagnet is this one where the spins are allowed to point in any direction they like. But in a ferromagnet, they all point in the same direction, and then you have the anti-ferromagnet, and then you have the ferrimagnet, and so on. The thing to appreciate is that the paramagnetic phase is more symmetric. The system is rotationally symmetric. It is invariant under a rotation. Whereas that rotational symmetry is broken in a ferromagnet. All the spins are pointing in a particular direction. Now, as I said, when this symmetry is lost, the rotational symmetry is lost in the ferromagnetic ground state, there emerges a new property. There is an emergent property which was not there in the high temperature phase, and that is the spin wave. So here is a system of chains in one dimension. For example, in the ferromagnetic state, I can excite a wave in which the orientation of the spin changes periodically in space and time, and these are known as spin waves, and these can be seen very easily in neutron scattering experiment of a ferromagnet. Now, in the case of a liquid-solid transition, the symmetry that is lost is the continuous translational symmetry of the Galilean invariance of a liquid. And the new emergent property is the rigidity of the solid. So the macroscopic rigidity of a solid, the reason why you don't fall through the floor of your living room, is because the solid is rigid. It is rigid because that rigidity is a consequence of the broken symmetry or the loss of symmetry. So here you have a normal liquid. Let's consider a molecular liquid. This consists of long molecules, like the shampoo you use to clean your hair. The reason why when you put shampoo in your palm of your hand, it is a whitish color, because the molecules have size comparable to the wavelength of light, and therefore they scatter light very effectively. Now, when I cool this normal isotropic liquid, in which the molecules can orient themselves in any direction they like, it becomes a liquid crystal. Now, it can become a liquid crystal in one of 4 different forms. It can form what is known as nematic liquid crystals, where all the molecules point in the same direction, but the center of mass of these molecules is not aligned in any particular way. Whereas I could have a spectic liquid crystal, in which all the molecules are pointing in the same direction, and it is arranged in layers, as shown over there. Then I can have a spectic C liquid crystal, which is again a layered arrangement of ordered molecules, but the orientation can be different in different layers. So what is lost in a liquid crystal compared to isotropic liquid is the orientational symmetry of the molecules. And in the case of superconductivity, as was first pointed out by Yoichiro Nambu at the University of Chicago, soon after the BCS theory of superconductivity was discovered, is that the superconducting ground state lacks the gauge symmetry of the Hamiltonian. And a consequence of this broken gauge symmetry is the phenomenon of superconductivity and the associated perfect diamagnetism or Meissner effect of the superconductor. So, to repeat once again, associated with the spontaneous symmetry breaking, which is associated with phase transition, there are emergent phenomena such as rigidity of the solid, superconductivity, spin waves, etc. Now, what we want to do, after refreshing ourselves with the concept that we discussed at length in the previous lecture, we now turn towards what are known as cosmological phase transitions. It is this cosmological phase transition, in particular the grand unified phase transition when the universe was 10 to the power minus 35 seconds old, that concerns us in this lecture. What we will be talking about is the spontaneous symmetry breaking at this cosmological phase transition and the emergent phenomena which is known as the Higgs mechanism in elementary particle physics. I tried to explain this in the previous lecture. We will not go back to that, but let's continue with the story for the moment. So let me now try to explain what I mean by a cosmological phase transition. Now, I'm going to plot the history of the universe at various times in the y direction over there. Here we are when the universe was 10 to the power minus 45 seconds old. This is known as the Planck era. The temperature of the universe was 10 to the power 32 Kelvin. Our dream, or rather our hope, is that when the universe was younger than 10 to the power minus 45 seconds old, there is a grand unified theory, a super unified theory, which unifies all the 4 forces of nature: electromagnetism, the strong nuclear force, the weak interaction force, and the gravitational force. As I said, such a theory doesn't exist today, but we believe that someday there will be such a unified theory. But it doesn't matter. Let us come to the time when the universe was 10 to the power minus 45 seconds old. What happened at that time, we believe, is that the grand unified force, which is a unified description of strong nuclear interaction, weak nuclear interaction, and electromagnetic interaction, the grand unified theory described by a standard model of physics, breaks away from gravity. So we believe that from that time onwards, gravity has been an independent and separate force. We have not yet constructed a quantum theory of gravity, therefore there is no question of unifying it with the grand unified theory. Now, let us proceed with the expansion of the universe. The important thing to appreciate is when the universe was younger than 10 to the power minus 45 seconds old, it was more symmetric than when it was older than 10 to the power minus 45 seconds old. Why? Because I'm no longer able to describe all the forces using a single theory. I need two separate theories. I need general relativity to describe gravity, and I need the standard model of physics to describe the strong, weak, and electromagnetic force. So it is a lower symmetry. So at this time, there has been a cosmological phase transition where certain symmetry is broken. When the universe was 10 to the power minus 35 seconds old, the temperature had dropped to a more modest 10 to the power 28 Kelvin, there occurs a second cosmological phase transition. What happens at this phase transition, this is the phase transition that Alan Guth was interested in, is that the symmetry of the grand unified theory is spontaneously broken and the strong nuclear force splits from the electro-weak force. So at times later than 10 to the power minus 35 seconds, you can no longer describe the strong nuclear force which binds neutrons and protons together with the same theory as the electro-weak theory. So you have two separate theories. Therefore, the time between 10 to the power minus 45 seconds and 10 to the power minus 35 seconds has a higher symmetry because there is a greater degree of unification. The state of the universe at later times has a lower symmetry because this higher symmetry has now been lost and you have now two separate forces. So this is the grand unified theory phase transition that Alan Guth was talking about. So what is the symmetry that is broken? As long as you have a grand unified theory, strong, weak, and electromagnetic forces, the symmetry underlying that gauge theory is what is known as SU3 cross SU2 cross U1. U1 is the symmetry of quantum electrodynamics. SU2 is the symmetry of weak force. And SU3 is the symmetry of the strong force. So SU3 cross SU2 cross U1 is the symmetry of the Hamiltonian and of the ground state of the grand unified theory. But above the phase transition, this symmetry is now reduced because the strong interaction is described now separately and it has an internal symmetry of SU3, and the electro-weak interaction is a separate theory and it has an internal symmetry of SU2 cross U1. Therefore, there is a spontaneous breaking of symmetry at this grand unified theory phase transition. And it is the emergent property at that phase transition that we are concerned with now. But let's proceed with further phase transitions that occur. Let us go to a later time when the universe was 10 to the power minus 10 seconds. Already, gravity has been a separate force all along, and the strong force split from the electro-weak theory at 10 to the power minus 35 seconds, which is the Guth phase transition. But electromagnetism and weak interaction continued to be described by the Salam-Weinberg-Glashow electro-weak unified theory. But at that time, 10 to the power minus 10 seconds, a third phase transition occurs where the electro-weak theory splits into electromagnetic theory and weak interaction theory. So there is now, today, in today's world, there are four forces. Today the universe is 10 to the power plus 18 seconds old, and there are four separate theories to describe the strong force, the electromagnetic force, the weak force, and the weakest of all, gravitational force. Because we have quantum theory for these first three, and we have only a classical theory for gravity. Now, let us look at all the symmetries that have been lost. So, at very early times, we hope someday we will have a unified super force which describes all four forces in a unified manner. And at later times, you have a grand unified theory whose symmetry is SU3 cross SU2 cross U1. That symmetry is then broken at this Guth phase transition when strong interaction go their own way and electro-weak theory goes its own way. And then later on, the electro-weak theory, once again, the symmetry is lost and electromagnetism splits from weak interaction. So SU3 cross SU2 cross U1 ultimately becomes SU3, SU2, and U1. So these are the various cosmological phase transitions that one expects at the times that I have indicated. Now let's come back to a story of inflation of the universe. And let's go back to Alan Guth. I said in Alan Guth in 1981 gave a plausible model for why the universe expanded exponentially at a rate faster than the speed of light, and that helped us to solve several problems with cosmology. He argued that the grand unified theory phase transition was one of those super cool phase transitions in which the universe was trapped in a metastable state or in a false vacuum. And it was during that phase when the energy density of the universe remained constant in time. There was an exponential expansion of the universe. So that is the phase transition we are talking about. Now, symmetry breaking and phase transition, we have now revised it twice now. So let's get on with the story now. In the grand unified theory phase transition, which we expect should have happened when the universe was 10 to the power minus 35 seconds old, the SU3 cross SU2 cross U1 symmetry is broken. Strong interaction splits from the electro-weak interaction. And there is an emergent property, like spin waves in a ferromagnet, like rigidity in a solid, like supercurrent in a superconductor. There is an emergent property. What is the emergent property associated with this symmetry breaking and with the Guth phase transition? That emergent property is the following. Till then, the fermions, the quarks and the leptons were massless. And you had massless scalar bosons, which are the gauge bosons of the theory. Now all these acquire mass through the Higgs mechanism, which I tried to describe in the previous lecture. So the Guth phase transition is the first order phase transition, like a liquid-solid phase transition, in which the free energy jumps discontinuously from one phase to another. But unfortunately, it gets trapped in a supercooled or a metastable phase, and the energy density associated with the scalar field, which has come to be known as the inflaton field, because it gives rise to inflation, horrible word, inflaton field, but there you have it, and the energy density associated with that dominates the universe. And when the universe is trapped in this false vacuum or metastable state, the energy density remains constant in time. Then Alexander Friedman, the universe expands exponentially many times, and you have the phenomena of inflation. So, to repeat once again what I discussed last time, in quantum theory, you have quantized fields. You have quantized electromagnetic fields, and you have quantized gauge fields. The excitations of these quantized fields are the elementary particles. Now, these elementary particles need not have mass. A photon doesn't have mass. But in most modern theories, there also occurs a homogeneous classical field phi that mimics the vacuum energy, the cosmological constant lambda of Einstein. It is a very large energy density, and it can remain constant because the universe is trapped in a metastable state. And it is this classical field which causes the exponential expansion of the universe. So after the symmetry breaking transition, when finally the universe quantum mechanically tunnels from this false vacuum to the true global vacuum, the inflaton field phi acquires a mass, and all the other massless fields that interact with the inflaton field, which is like the Higgs gauge field, like the Higgs boson, also acquire mass. Therefore, the effective mass of the particles acquire mass. So let me say it once again. After the symmetry breaking transition, massless particles, fermions and bosons, which interacted with the field phi, acquire mass. Why do they acquire mass? Because when the universe tunnels from this metastable false vacuum to the global vacuum, the free energy functional can oscillate about this minimum value. Now that is like a simple harmonic oscillator in the potential half kx squared. All right? And you know that the frequency of the simple harmonic oscillator is related to square root of k over m. So frequency and mass are synonymous. So in other words, because the universe now has reached this global minimum, but it can oscillate now about this global minimum, you say it has a certain mass, just as the simple pendulum has a mass. And that mass is, the amount of mass is decided by the curvature of this potential around the minimum. Okay? So it is determined by the second derivative of the potential around the minimum. But if you didn't understand the statement, just ignore it. I'm merely trying to say is that after the spontaneous symmetry breaking phase transition, the grand unified theory phase transition, particles acquire mass. So all the energy that was in massless fermions and massless boson is now converted to massive fermions and massive bosons, and we have the universe of elementary particles. So that is the paradigm of elementary particle physics today. So the emergent property due to the spontaneous symmetry breaking is the masses of elementary particles. All right? So the Higgs mechanism tells you how massless fermions and massless bosons become massive fermions and massive bosons. So this mass is an emergent property, just as rigidity is an emergent property, just as spin wave is an emergent property, just as supercurrent is an emergent property. In a similar manner, the masses of quarks and leptons is an emergent property associated with the spontaneous symmetry breaking that occurs at the grand unified theory phase transition. So this is how material particles of the universe was created from vacuum energy. Of course, there are equal number of particles and antiparticles, but our present-day universe does not have an equal number of particles and antiparticles. There is a small excess of particles over antiparticles. Why there is this asymmetry is still an unsolved problem. Remember, this mechanism will produce an equal number of fermions and antifermions, of quarks and antiquarks, of baryons and antibaryons, leptons and antileptons. Why there is a net baryon number, why there is a net lepton number is still not fully understood. So let's leave it as one of the unsolved problems of physics. So inflation is a stage of accelerated expansion when gravity acted as a repulsive force. So y-axis is the scale factor of the universe, x-axis is the time, till about from around 10 to the power minus 35 seconds to 10 to the power minus 36 seconds, there is an exponential acceleration of the universe, followed by a power law deceleration of the Friedman-Robertson-Walker models. It's either R is proportional to square root of T if it is radiation dominated, or T to the power 2 by 3 if it is matter dominated at later times. So that's the phenomena of inflation. Why is this phenomena important? Because it enables us to understand the observed isotropy and homogeneity of the cosmic microwave background radiation. Causal connection had somehow got to be established between different parts of the universe. That is only possible if at some early time the universe expanded faster than at the speed of light. So you needed a phase of exponential expansion to explain the observed homogeneity and isotropy. Secondly, the geometry of the universe is Euclidean, it's flat. Such an exponential expansion would make the universe flat no matter how crumpled it might have been initially. Right? So those are the attractive features of the inflationary phase. And third, perhaps the most important consequence of inflation is that it gives us a handle for primordial density fluctuations, which then grew initially linearly and then non-linearly and formed the large-scale structure of the universe, which then cascaded down to clusters of galaxies, to individual galaxies and stars. So inflation, although it is still only a plausible model, has many attractive features. It shouldn't be a dogma like it is projected to be by the practitioners of the theory, but you have to admit that it has many attractive features. But there is a problem, a serious problem with this idea of inflation. And that is the following. In a second order phase transition, for example, between a paramagnet and a ferromagnet, when the transition occurs, the spontaneous magnetization is pointing in the same direction throughout the sample. All right? In other words, the new phase is a homogeneous phase, and the value of the order parameter is the same everywhere in the sample. But this is not true of a first order phase transition. And remember that the grand unified theory phase transition is a first order phase transition. Even worse, it is a supercooled phase transition, where the universe is trapped in a metastable state. And as I told you, a first order phase transition occurs through nucleation. Remember the examples of droplets of liquids forming before the whole vapor becomes a liquid. All right, now here is a problem. So what do I mean by nucleation? An isotropic liquid forms droplets of liquid crystals, and finally the whole thing becomes a liquid crystal. A vapor forms droplets of water, and then these droplets grow in size, and eventually you have water everywhere. So in our case, what will happen in a first order phase transition, when the universe tunnels from the metastable minimum of the free energy to the global minimum, you'll have bubbles of the new phase forming. And the value of the scalar field in each of these bubbles will correspond to the value corresponding to the global minimum. Phi will be equal to phi naught, not the value it had in the false vacuum. So you have a problem, and let me explain that problem using some figures. So here you have the false vacuum, and the false vacuum nucleates into bubbles. So if you like, let us say that the green sphere is your water vapor, and these magenta bubbles are droplets of water that are appearing. So in a first order phase transition, these droplets appear, disappear, appear, disappear, grow in size, and the whole thing becomes more and more sluggish, till finally all the droplets coalesce and you have water everywhere. So this is the true vacuum. These are the bubbles of nuclei of the new phase. And this is the false vacuum. But please remember that this false vacuum is expanding exponentially. It's expanding as e to the power h times t, where h is the Hubble constant, and it's determined by the energy density rho. Whereas this false vacuum, the true vacuum corresponding to the global minimum of the free energy, which are bubbles of the new phase, they will be expanding according to power law, square root of t or t to the power 2 by 3. So the true ground state of the universe, which are these bubbles, will never coalesce to form a big homogeneous universe, and we reside in this small little portion of this homogeneous universe. The point I'm making is that this will not happen. This will not happen because the false vacuum would have continued to inflate, and the distances between the bubbles will increase exponentially. The bubbles will never coalesce and merge. Right? Fine. So let's go back to the liquid vapor to water transition. What we said was droplets of water form, bigger droplets appear, droplets coalesce, and this cascades till finally the whole thing becomes a liquid. Suppose, just suppose, unlike in the thermodynamic phase transition case, the space between the droplets of water, which is the water vapor, suppose that space expands exponentially, then the droplets of water will never coalesce, will they? and you will never have the vapor to liquid phase transition. In a similar fashion, I'm saying this will not happen. What will happen is that, yes, bubbles of the new phase will form, but these bubbles will be expanding as a power law, Friedman, Robertson, Walker models, but the false vacuum, which is the region in between, is expanding exponentially fast. So these bubbles will never merge, and this will not happen. So this fatal difficulty, truly fatal difficulty with Guth's model of inflation, was first pointed out by Stephen Hawking and his collaborators soon after Guth's paper was published. But it doesn't matter. Within a year, Linde, a Russian theoretical physicist, now at Stanford University, and Albrecht and Steinhardt at Princeton University in the east of the United States, came up with a new theory of inflation which took care of Hawking's fatal objection. It was a beautiful, elegant, and yet very simple explanation. So let me explain this to you. This is known as slow roll inflation. Now, what I plotted here is the potential energy or the free energy of the universe as a function of the value of the scalar field phi. Previously, in Guth's model, there was a shallow minimum, and the universe was trapped in that shallow minimum, which was the super cool metastable state. And then the universe tunneled from there to that global minimum. And suddenly you had bubbles. Inside each of the bubble, the value of the scalar field now corresponded to the value at the global minimum. And that's what caused us problems. Now, what Linde and others said was the following. Suppose the value of the scalar field does not change dramatically from there to there, but changes very slowly, like a ball rolling down a slight slope. There is no large barrier through which there is quantum mechanical tunneling. There is just a slight slope, and the value of the scalar field, yes, it decreases, but it decreases very slowly with time. It decreases quasi-statically. Therefore, it is almost as though with time, when the value of phi changes with time, it is not changing at all. And therefore, the universe will continue to, the bubbles will continue to expand exponentially. So the scalar field phi rolls slowly from phi equal to 0 to phi equal to phi naught. All along, as it rolls, because the value of the scalar field changes only quasi-statically, the bubbles will continue to expand exponentially. And then eventually, the value of the scalar field will correspond to the global minimum value. But by the time each bubble is expanded exponentially, then you will have a very large homogeneous universe, many such bubbles. So let me try to explain this one more time using this figure. This is Guth's inflation. There is a metastable state, overly stable false vacuum, and then there is quantum mechanical tunneling, and the universe plunges from that metastable state to this global minimum state, essentially leaving all the energy in the bubble walls, where all the latent heat is now frozen in. The universe is essentially empty, cold, devoid of any massive particles. So you don't have the universe we observe today. But in the slow roll inflation theory of Linde and Albrecht and Steinhardt, what happens is the universe rolls slowly from there to there, and in the process, because the value of phi changes very slowly with time, each bubble now expands exponentially, a la Friedman, Robertson, Walker. So let me now state this pictorially. One picture is worth 10,000 words. Remember the ancient Chinese saying. So here is one bubble in the false vacuum, one of those many, many bubbles. The value of the scalar field in the false vacuum is phi equal to 0. The value of the scalar field inside this bubble is not strictly 0, but it is very nearly 0. So there's a slight tinge of magenta I have shown over there. Now this bubble is inflating like mad. According to theory, the initial size of the bubble is around 10 to the power minus 20 centimeters, and it expands to about 10 to the power 800 centimeters. It will eventually expand. It's still expanding. Each bubble is expanding. Our universe is only 10 to the power 28 centimeters at the moment, corresponding to an age of 10 to the power 18 seconds. All right, now this bubble has expanded to an even larger size. It has expanded exponentially. The value of the scalar field inside has changed very slightly. So it's a little more magenta now, but it's still expanding exponentially. It is still essentially false vacuum. The value of the scalar field inside each of these bubbles, I've only shown one bubble. There are millions of such bubbles corresponding to millions of droplets of water in the vapor-liquid phase transition. The value of the scalar field in each of those bubbles is still very nearly 0. Each bubble has now become exponentially large. Finally, the value of the scalar field decreases to the global minimum value, and the value of the scalar field now corresponds to the global minimum value of phi equal to phi naught in each of those bubbles. So this is a homogeneous universe. Each bubble is a homogeneous universe, and the value of the scalar field corresponds to the value of the scalar field of the global minimum. So using the Higgs mechanism, all the energy in massless fermions and massless bosons have been converted to massive fermions and massive bosons, and we have created a universe with massive particles. So here are the various bubbles. Nucleation in a first-order phase transition. The region in between is the false vacuum, still expanding exponentially. Each bubble is still expanding, but now as a power law. And we happen to live in a small region of one of these bubbles. All right? So the universe that we see is not the entirety of the universe we belong to, but that whole region is homogeneous and isotropic. So that's the new inflation theory. So let me say it all over again, this time in words. Like in Guth's inflation, the new inflation of Linde and Steinhardt is also associated with the grand unified theory phase transition at t equal to 10 to the power minus 35 seconds. And it is associated with the spontaneous symmetry breaking at that phase transition. SU3 cross SU2 cross U1 splitting into SU3 and SU2 cross U1. Now the potential for the scalar field as a local minimum, like in Guth's model, but the potential barrier is very small, so there is no need to invoke a quantum mechanical tunneling. So there is a gradual rolling of the universe from the metastable state to the globally stable state. Again, the phase transition is through nucleation and formation of bubbles. But the scalar field inside the bubble starts out with a value very nearly equal to 0 because phi is changing very slowly with time, and therefore it's expanding exponentially. Eventually, since the scalar field is changing very slowly with time, it is very nearly constant, and therefore the bubbles also expand exponentially, just as the false vacuum is expanding exponentially. Eventually, the value of the scalar field inside each of these bubbles slowly grows, and each bubble is now filled with energy corresponding to the global minimum, and this energy is now converted to particles, baryons and antibaryons, leptons and antileptrons. And now this bubble will now expand as a power law, T to the power 1 by 2 in the radiation-dominated universe. Our universe is supposed to be a small part of one such bubble. So before we end, let us try to summarize what are the underlying assumptions of the theory of inflation, either Guth's theory or the modified new inflation theory, which seems to have solved the problem posed by Stephen Hawking and his collaborators. So let's state the underlying assumption of inflation once again for the last time. We have assumed that the universe was in a state of thermal equilibrium already by the time of 10 to the power minus 35 seconds. The universe was homogeneous and isotropic, and it was large enough, to have survived. Because if gravity had been a little stronger, as I explained in one of the earlier lectures, the universe could have collapsed before 10 to the power minus 35 seconds. So luckily gravity was weak enough that the universe survived till the time of the onset of inflation. Remember the fine-tuning problem that we discussed. That's what I'm referring to over there. Then we have assumed that the scalar field was constant over space and time. So that is zeroth law of thermodynamics. In thermal equilibrium, the value of the density will be the same everywhere. The value of the temperature will be the same everywhere. In a homogeneous, in a thermodynamic state which is in equilibrium. Then the universe expanded and cooled, and it underwent a phase transition associated with the spontaneous symmetry breaking. The strong force and the electro-weak force split at 10 to the power minus 35 seconds. The free energy was caught in a metastable state, or a false vacuum, as elementary particle physicists would like to call it. This is like a vapor being trapped in a supercooled phase, or a liquid being trapped in a superheated phase. The universe expanded exponentially while trapped in the metastable state, because all you need for exponential expansion is the energy density being constant in time, because the expansion rate of the universe h is related to the energy density. So if the energy density is constant, expansion rate is a constant, and the scale factor of the universe will expand as e to the power ht. And since h is a constant, it's an exponential expansion. The universe expanded exponentially when trapped in the metastable state. It now seems that all these assumptions may not be necessary after all. And this I shall explain in the next lecture. All one needs, it now turns out, is small patches of the universe, whose volume is 10 to the power minus 33 centimeters, 10 to the power minus 33 centimeters, 10 to the power minus 33 centimeters, or the Planck scale size universe, in which the scalar density is uniform, in which the value of the scalar density is very large, and it remains constant in time for long enough, then that small patch of the universe will expand exponentially. So it looks like that patch of the universe will expand, and it will expand exponentially. So let us see how this works. And that I shall describe in the next lecture, which will also be the final lecture of this series. So before I make one or two comments about it, let us recap and summarize what I have tried to say in this lecture. The basic problem with the Big Bang cosmology were the following. Why is the cosmic microwave background temperature the same in all directions? There couldn't possibly have been causal connection between the different parts of the universe, even in the distant past. Why is the geometry of the universe flat? Why are there no magnetic monopoles in today's universe? Why the universe today is dominated by baryons and not antibaryons, leptons and not anti-leptons? Why is the symmetry between particles and antiparticles broken in the universe? Why there is an expansion of the universe in the first place? These were the questions. And the model suggested by Guth and improvised by Linde and Albrecht and Steinhardt in the new theory of inflation seems to have solved this problem. But as I will explain in the next lecture, you don't even need all these fancy theories. It looks like inflation is a very generic phenomenon, but we will not anticipate that right now. So before we begin in the next lecture, I will have some important announcements to make. Till then, thank you very much for your kind attention.